we're now going to generalize some of the results about powers and orders that we introduce for permutations to arbitrary groups. So here is the definition. We take a group G star, like this, with identity E, and we let lowercase g be an element of this group, and n be an integer. We're going to define the power g to the power n. And we do this, like we did for permutations, in 3 cases, according to whether n is positive, whether n is 0, or whether n is negative. So first of all, if n is positive, then g to the power n is defined to be g combined with itself n times using the group operation. So we could write this as g star g star g star g star g, where there are n g's. Next, if n is 0, we define g to the power 0 to be the identity element. So E here refers to the identity element of the group. And if n is negative, then we define g to the n to be the inverse of g, combined with itself n times, or minus n times rather, using the group operation star again. So this is exactly the definition of a power of a permutation, except with composition replaced by whatever the group operation happens to be. So let's look at an example. We're going to look at an example where the terminology of powers is a little bit misleading. I think it's important to do this example because otherwise it can be quite confusing. So let's think about what happens in Z. So the group of integers under addition. So in this case, taking a power is a very confusing piece of terminology, because what you're doing when you take a inverted commas power is combining something with itself multiple times under by using the group operation. So in Z plus, and let's put this in commas, nth power of 1, for example, would be, well, if n is positive, and let's assume it is for now, if n is positive, the nth power of 1 would be 1 plus 1 plus, and so on, n times. So that is, of course, n. On the other hand, the 0th power well, that will be the identity element of this additive group. So the identity element of the group of integers under addition, and that will be 0. And if you had a negative number, n, then the nth power of 1 will be n again, because you will be adding minus 1 together, minus n times. So the result is minus n, or is n. Okay, so those are our examples of powers of a group element. And just as for permutations, the exponent laws again hold for arbitrary groups. So by the exponent laws, I mean the following 2 statements. If you take a group G, you take an element, lowercase g, of that group, and you take 2 integers a and b, whether they are positive or negative or 0, the following rules always hold. So g to the a times g to the b, or g to the a combined with g to the b under the group operation. So when I'm writing these things next to one another, I mean combine them using the group operation. Then the result is g to the power a plus b. And secondly, if you do g to the power a, and then you raise that to the power b, then that's the same as doing g to the power a multiplied by b. So here a times b, this is a and b multiplied together using ordinary integer multiplication. Now in particular, that tells you that the inverse of g to the a is g to the minus a, because if you multiply g to the a by g to the minus a, then according to the first exponent law, you get g to the a minus a. And of course that's g to the 0, and that is e. So the inverse of g to the a, no matter which integer a is always g to the minus a. Again, we're going to directly generalize the definition of order which we gave for permutations. So if you take a group G, which has identity element E, like this, and you take an element lowercase g, big G, then the order of lowercase g, which we write like this, is defined to be the smallest positive integer n such that g to the n is equal to the identity. So it's not necessarily true that such an integer n always exists. If no such positive power of g equals the identity, then we say g has infinite order, and that can happen. So let's make a couple of observations, of examples. So first of all, the only element whose order is 1 is the identity, because the first power of g is just g again. So if the first power of g is equal to the identity, then g itself is the identity. So the only element with order 1 is the identity element. Okay, some other examples. Well, you know lots of examples already because you've already studied this context, this definition in the context of permutations. So for example, any n cycle has order n. If we look at an example of something with infinite order, well, let's look in the group Z under addition again. So in Z plus the element 1 has infinite order. Because if you add 1 to itself any number of times, you never get the identity, which is 0. So the element 1, and in fact any non-zero element of the group of integers under addition, will have infinite order. On the other hand, for an example of an element with finite order, take any permutation. It's got finite order, and for example, a 3 cycle would have order 3, a 5 cycle would have order 5, a transposition would have order 2, and so on. So what we'll prove now is that actually every element of a finite group must have a finite order. So if you take an element of a finite group and you think of its powers, g, g squared, g cubed, g to the 4, and so on, then at some point one of those powers must be equal to the identity. So why is that? Let's think about the elements g, g squared, g cubed, and so on. Now, eventually there must be a repeat on that list of elements. It can't keep being new elements forever, because there's only finitely many different elements in g. So you can't have an infinite sequence of elements of g being all different. Eventually there must be a repeat on that list. So if there's a repeat, what that means is that g to the I is equal to g to the j for some I less than j. Now if that's true, let's do a calculation. Right? If g to the I is equal to g to the j, then I can multiply both sides by the inverse of g to the I. And the inverse of g to the I is g to the minus I. So if we multiply both sides here by g to the minus I, then what happens is we get g to the minus I times g to the I is equal to g to the minus I times g to the j. Okay, well, use the exponent laws. So what do I have on the left? On the exponent laws tell me on the left I've got g to the I minus I. And on the right I have g to the j minus I. So that's two applications of the first exponent law. But on the left, g to the I minus I, that's g to the 0. And g to the 0 is by definition the identity element. So here I'm using e to refer to the identity element in g. Okay, so we established that g to the j minus I is equal to the identity. So that's some positive power of g equal to the identity. And so the order actually exists because the order is defined to be the smallest positive power equal to the identity. And since there is some positive power of g equal to the identity, well then there must be a smallest power of g equal to the identity. So the order of g exists, but it's a finite number, and in fact it's at most j minus I, whatever that was. So we can say something about the first n minus 1 powers of an element with order n. So the lemma says if you have an element lowercase g of a group which has order n, then all of the powers, g to the 0, which is the identity, then g to the 1, g to the 2, up to g to the n minus 1, those things are all different. So before we do the proof, let's remind ourselves of the meaning of saying the order of g is n. What that means is n is the smallest positive power of g equal to e. So n is the smallest positive number, such that g to the power n is equal to the identity. So I claim that all of those powers of g must be distinct. And to show this, we can do actually the same calculation that we did on the last slide, which is, let's suppose they're not distinct. Well, yeah, let's suppose they're not distinct. So we'll suppose that g to the I is equal to g to the j for two different numbers I and j between 0 and n. So greater than or equal to 0 and less than n. And since one of the I and j must be bigger and the other must be smaller, let's say I was less than j. Well, in that case, by the exact same calculation that we did before, g to the power I minus j is equal to the identity. But if it's equal to the identity, well, j minus I is less than n, because j was less than n, and j minus I is even smaller than j. So j minus I is smaller than n, and that contradicts n being the smallest positive power of g equal to the identity. So I guess we should also notice there, because j was bigger than I, j minus I was also bigger than 0. So this contradicts n being the smallest positive power of g equal to the identity, and therefore no such pair exists. And those powers, e, g, g squared up to g to the n minus 1, those things are all different. And in fact, even better, you can show that any power of g is equal to one of these things. So that tells you there are only n distinct powers of this element g with order n. And the reason that this is true is because if you take any power of g, so let's say g to the a, so where a is any integer, we can divide a by n and get a quotient and a remainder. So we can divide a by n to get a is equal to something times n plus a remainder, where the remainder is always greater than or equal to 0, but less than n. And now if you look at g to the power a, so g to the power a is g to the power qn plus r. And we can use the exponent rules to write this as g to the qn times g to the r. And we're going to use the exponent rules again and write this as g to the n to the q times g to the r. Okay, but what is g to the n? It's the identity, because g had order n. So what you've got there is the identity to the power q times g to the r. But if you compose the identity with itself a bunch of times, then you just get the identity again. So, because the inverse of the identity is the identity, if you compose the inverse of the identity with itself a bunch of times as well, you also get just the identity. So this is just the identity times g to the r, and that's g to the r, right? And g to the r is one of the things on the list right here. So we've shown that actually any power of g, so g to the a for any integer a, is equal to one of the things on that list. So every power of an element of order n is equal to one of the powers, g to the 0, g to the 1, g to the 2, up to g to the n minus 1.